Okay. So yeah, when you tell me you like things and when you tell me you don't like things, I like hearing both of those things from you. So keep that up. Um, so what we started talking about last class was this main tension between what we have in our data sets, the samples, and the population, right? So we walked through this main tension. You all had just taken a mini exam, so I expect like this may have bounced off the side of your head and gone back into the void. So I just wanted to walk you through a little bit of what we did. So the main idea is, we've spent all semester summarizing data, and I think summarizing data is interesting, right? Like we can do all this like actual work with data sets. But when it comes down to it, we don't particularly care about what's in the data sets, right? The data sets tell us something, but what we want is information about a population, not just summarizing what's in our data set. So we walked through this whole thing of like measuring measures of location, your standard sample mean. And then we talked about how we would construct a measure of dispersion. So how spread out is the data? And we walked through this whole thing, just almost like the historical set of steps that we've taken to arrive at the standard deviation as our main measure of dispersion. But then the core idea is the questions we've been asking so far in this semester are essentially like differences in samples. So this was our old question: which sample sleeps longer? Question about the data. But in general, when we're asking questions, right, like our motivating question at the beginning of the semester was, does the minimum wage lead to higher levels of unemployment? This is not a question about did higher minimum wage lead to higher levels of unemployment, specifically in the 90s in New Jersey and Pennsylvania. Like, interesting question for sure, but the main question is like, is our model correct? And that's something we can only infer from the data, right? Like the answer to is minimum wage going to lead to unemployment? That's a very general question, and that's not something that that's not a question of the sample. That's a question of the model. And so our questions now are turning from summaries of our data sets to how do we take a data set and make inferences about a population, which is, I think, conceptually a much more challenging thing to do. So this is the idea. We have our population. We don't know what the population looks like. The population, no matter what we're studying, will be unobservable to us. What is observable is the sample. And so we talked through this distinction. The notation we use for the sample is x bar for the sample mean, and the sample standard deviation is s. Then we have mu for the population mean, and then sigma for the population standard deviation. So these are the measures of centrality and dispersion for the population and for the sample. So our main thing is, the main tension is we observe the samples and we study the populations. So that's the fundamental tension. We talked through some of the notation or terminology. We talk about a random variable as the data generating process. It's like, how does the data arrive? Like so a random variable for, how many people are walking past you on the sidewalk. There's like a way that the data arrives, right? So it's like, how many people are arriving in every minute walking past you on the sidewalk? There's a process that generates how people walk past you. And it's fundamentally random. So that's essentially like a deck of cards. We have a probability mass or density function. We just call this probability density function. Just a function that assigns probabilities to any particular outcome. So it's like with a standard deck of cards, it's 1/52. Is the probability we would draw any one of the cards. And then the observation is just the realization of a random variable. So I draw a card, and then I write down what was on the card, and then I put that back in. The sample, what we call data, is just I do that over and over again, and I write down each of the cards. And this is the thing we observe. But the fundamental tension, right, is we have this, which we never observe, the probability distributions. And this is what we have questions about. What we observe are the samples. So we've talked about all of the ways that we think about summarizing in useful ways what's in the sample. But where we're going is trying to use that summary to make claims about something we don't observe. Yeah, this is, I think, one of the big tools we have at our disposal. I'm just constantly amazed at what we can do. All right, so that's the main idea. We talked about a few probability functions. I think a lot of you have seen these before. We're going to spend a little more time working with them. But the main one we'll work with is the normal distribution. Raise your hands. How many of you have seen or worked with a normal distribution before? Okay. Almost everyone in your stats class probably. A uniform distribution, how many have worked with one of these before? It's a little less common. It's the simplest and easiest one to work with. What about an exponential? How many of you worked with an exponential? Nice. Chi-square is maybe more common than exponential. Hands up for chi-square. Yeah, there's specifically a chi-square test, which is a certain kind of test. We're not gonna, the thing we're doing can run a chi-square test, but we're not gonna talk about it that directly. And then there are these discrete probability functions, or probability mass functions, binomial and Poisson. Today we're gonna work with chi-square and normal in the second part of what we're doing. But I think just as I wanted to review a bit about probability density functions and cumulative density functions, which we're going to spend some time thinking about today. So probability density function is just, we call it a PDF, not to be confused with the file system, blanking on what it's called, portable document manager, portable document file, PDF? Format, yeah, there we go. So this is just a way of thinking about probabilities. The height of the function just assigns a number to every specific value. And the way PDFs are set up, we just need every value on the domain to have a non-negative value. So we just need every value of f to be positive. And then we need the integral over the entire area to sum to 1. So this is essentially just saying, when we take all the probabilities, it has to be equal exactly to 100. So the total probability must sum to 1. Those are PDFs. Cumulative density functions, how many of you are familiar with CDFs? Okay, fewer than I would expect, but that's all right. We're just gonna do a bit of review here. This is how we work with sort of areas under the curve. Thankfully, there's a lot of nice structure for how we think about finding areas. This is what we call a cumulative density function. It's the area under the curve up to a specific value. So little f is our PDF, big F is our CDF, the cumulative density function. It just tells us the probability that the value is less than or equal to some value. So it's essentially, I think in terms of visuals generally, the CDF just tells us the area under the probability density function up to some x, whatever that is. So in this case, this is a picture of the CDF of 6. So this is the CDF of 6. As you would expect, the CDF is non-decreasing. So as we increase on the horizontal axis, so as x goes up, the area under the curve will not go down. And that's just because no value of f can be negative. So if we're integrating over larger and larger areas, all of which are positive, then the CDF is non-decreasing. And then the CDF at at negative infinity is 0. So if we're like all the way out to negative infinity, the area under that curve is, of course, going to be 0 because we're not integrating over anything at all. And then if we continue increasing our x out to positive infinity, then we're just going to integrate over the entire PDF, and that's going to give us exactly 1. The area under the curve must be equal to 1 by definition. Okay. And then we can just always find the probability less than some number using this CDF. And this is going to come in handy when we're thinking about areas under the curve of known distributions. Okay, any questions here? We started working with some of this, but I just wanted to sort of double back. I sensed we may need a bit of a refresher to think about CDFs. Okay, so this is what we did at the beginning of class last time. I'm sorry, the end of class last time. Y'all want to take bets on whether the exercise link works? It does, yeah. Okay, so wouldn't that be what a tragedy if it didn't? So this is the first thing we're going to do. I just want to spend a few minutes just refreshing our memory on how to work with known distributions. In general, we're not going to know the distribution of the population, but it will be important to be able to work with known distributions. So here we have County A's sleep time. So each data point is xi, our standard notation from the first part of the semester, standard statistical notation. And then we're saying it's normally distributed with a mean of 7.2 and then a standard deviation of 1.5. And my question is, what proportion of the population sleeps less than 5 hours? We've talked a bit about this, right? Like I've shown you some pictures. So let's treat this as a bit of a warm-up. I want you to, even though I've shown it to you, that was 2 days ago, try to draw a picture of what this looks like. It doesn't need to be, I'm not looking for a number yet. You can calculate a number if you wish. But in general, when we're thinking about these areas or these probabilities, it's a good idea to think in terms of visuals, as it usually is. Try to draw a picture, either on a piece of paper or in your head, and then tell your neighbor what the picture looks like to answer this question. And then we're going to actually calculate. Should we take 2 minutes? Tell your neighbor they did great on the mini exam, and then try to answer this question with a picture.
Direction is one standard deviation, 68%. And then 99.7. So it's 68. Yeah, that'd be one standard deviation of 68. Divided by 2, which is less than 5 hours. Like, theory 34%. There's that. It's not.
Okay, someone want to help me out here? What's the picture we have in our heads when we try to answer this question? Pete?
I don't know what kind of distribution this would be, but it would be a graph where the distribution would be.
Yeah.
And then that on the x-axis up to 5 hours would be shaded in, and
Okay.
anything greater than that would sort of be left out.
Yeah. So in this case, we know exactly what the distribution is. This is just notation for normal. If I didn't spell that out, we wouldn't necessarily know what the shape is, but we could still, draw our picture. So what Pete is saying is anything under the curve up to 5 would be shaded in. So something like this. This is specifically a normal distribution centered on 7.2 with a spread of 1.5. Okay. Any questions here? Okay. So how do we calculate this? Yeah, Andrew.
I remember it's that it was some sort of some empirical rule or something.
Yeah.
Or if it's one standard deviation away, there's I think 68% of the population is within that 2 ways.
Yeah.
8 or whatever it was.
Yeah.
And so forth. So if you're trying to find what is outside of the distribution on one side, if it's only one standard deviation away,
Yeah.
then that's 68% are within the distribution.
Yeah.
And then it's trying to go to one side, divide that by 2.
Yeah.
34. And if it's like 50% that's on one side, do 50 minus 34 to get the 16% on the outside on the left.
So nice. So Andrew's walking us through, like, if we know how many, look, we can answer questions about how many the area under the curve at certain standard deviations, sort of standardized on either side. This is, sometimes we call this the empirical rule or the 1, 2, 3 rule. Goes by a number of different names. In this case, this is not, so like 5 is not a sort of an easy standard deviation away from the mean. So sometimes we can answer those kinds of questions using the empirical rule. In this case, we actually don't know the area, like 1.2 or what, 2.2 away from the mean would put us at 5. And we actually don't have very nice ideas for that. You can go to the back of the textbook and answer, like look up a table. You can like convert to a z-score and do all of that stuff. The good news is that I'm not going to ask you to do any of those kinds of things in this class. That's not what we're testing. We have a stats textbook, and we can just check the numbers in the back if we wished, convert to a z-score, or we could just have a computer run these things for us. A computer is basically doing the same thing as going to a stats textbook and looking at the table. These are like equivalent skills. So what we're going to do is actually run this calculation. So what we're going to do with code is just ask Python to find a normal distribution, get the CDF, the cumulative density function, and then enter into the CDF a value of 5. So you'll remember, a CDF just tells us the area under the curve up to some number. We just tell it what number to check. In this case, that's 5. So the next question is to actually find an actual number. So the way we do this, you all know how? Go to the course website that you've pinned to your browser this semester. You can unpin it next semester, and then click on Notebook, and that will bring up this thing. We go up here, File, Save a Copy in Drive. I don't get lecture points because the link actually works. And then we're going to run a few things. So actually try to use the code I've given you in the slides to try to find an actual number, like an exact number for the area under the curve, up to 5 minutes. So we'll take a minute here. Okay, maybe that's not quite a minute. At this point, I've given you all the code, so really all you have to do is just run the CDF to find the number. If you were stuck and you didn't have my slides, you could just ask Gemini. So like, find the CDF of 5 using a normal distribution and parameters above. So I've given you the parameters here, and then Gemini would probably be able to do it. But we can just copy this. So this is just using the Python stats package, stats, which we've imported, scipy import stats, and then we're getting a normal distribution. We're getting the CDF of that normal distribution. We're checking the CDF of 5, and then we're using the mu. So we defined mu to be 7.2 and then sigma to be 1.5, and then we're just getting that number. Any questions here? You think you can do a harder one? Okay, nice. Love that enthusiasm. We have 2 more questions, and then we're doing the big simulation for the day. Okay, so this is the warm-up question. What about this one? So this is not going to have quite as simple a solution. You're going to use a CDF. But the question is, what proportion of the population sleeps more than 9 hours? So the answer to the last question, right, was this number. This is a proportion of the population. So it's like 7% of people in this fake data set sleep less than 5 hours. Sleeping less than 5 hours is terrible. I hope everyone's getting much more sleep than that. How many people are sleeping a very long time? So more than 9 hours. Take about 2 minutes here. The first step is to just construct a figure for what you're trying to do, and then use a CDF to find the number. So I'm looking for both a picture and a number. As you're working through this, check with someone about your figure, and then check with someone about your approach. 2 minutes.
How can we get a figure for this? Because we're on, like, it's just an output versus output.
Yeah, so I'm not necessarily asking you to make a figure in Python. You can draw it on a piece of paper. This is a great mini-exam question, like draw a figure.
Yeah.
But yeah, you don't need to be able to do this in Python.
I didn't even get out.
Okay. Can I see?
I just typed it because oh, we're on this section.
Yeah, but don't just copy it.
Okay.
Try to figure out what to do. Yeah.
So I was trying to look stuff up for it, and because I'm trying to intelligence like what would make the engine theory make the code say go to the left of X or to the right of X.
Yeah.
So it said like CDF just go to the left of X, and then S just go to the right of X.
Yeah, so you can use SF. That's what's survivor function. You can do it with a CSNAP, which is the more standard approach. You have SF because we like shortcuts. Let's try with that. Okay, if you're still working, keep working on what you're doing. I know a lot of you are taking the code from my slides in advance. I don't recommend that approach. Feel free to do it if you like, but I sort of reveal stuff one item at a time because that's the way our brains work. So my first question is, how do we draw the picture? Like, if I were to ask you this for a picture hand-drawn on a mini-exam like this, how would we do it?
You have the normal distribution and then shaded all the way past it.
So something like this. So normal distribution, centered, spread the way we do, and then everything under the curve, but greater than 9 in this case. So using a CDF, how would we go about finding this area? Like, how do we think about CDFs in relationship to this kind of question? Yeah, Kim.
The CDF is cumulative, so it would be 1 minus the population that claims less.
So this is great. So the CDF tells us the area under the curve up to some value. So it's cumulative. So it's everything up. If we were to plug in the CDF of 9, it would tell us everything in white under the curve, which is sort of the opposite of what we're looking for. What Kim is realizing is the area under the curve, the entire area under the curve is 1. So the area in red is everything that's not up to the CDF, the CDF of 9. So if we subtract the CDF up to 9 from 1, that leaves us with the red area. Any questions about that? So to write this out, this would be like 1 minus the CDF of 9 would give us the answer to this question. And we can just do that exactly like we did before, just we found the CDF of some value. In this case, we're just subtracting it from 1. And that gives us the proportion of the population that sleeps more than 9 hours. Any questions here? Okay. My job is complete. I've put you all to sleep. Okay, so all I'm going to do is just run this thing. I get the proportion. Not that many people sleep more than 9 hours. What about this last one? There is code in the slides, and I know if you click forward, you can see it. My first question to you is, how much sleep does the middle 92% of the population get? This is the trickiest of the 3 questions. The first place to start with these questions is to draw a picture. We use visualizations because our minds are just good at thinking in pictures. So draw a picture and then maybe think about how you might use a CDF to answer this question. Or I guess not a CDF, but specific values. Or do y'all just want to do it on screen? Okay, let's do it on screen. So the picture I have in my head is like, this is the middle 92%, so it's going to be like the area closest to the middle. So we have these like tails, and we're not going to include them. And the tails in total need to add up to 8%. So it's like what's left over after we look at 92. So if it's 2 tails and they both add up to 8, then each tail separately would be 4%. So we want to look at the area sort of in the middle, excluding the tails. And we need these to be at exactly the 4th percentile and then the 96th percentile. So we need 4% to be less and 4% to be greater. So Python actually has a very convenient way of handling this. It's almost like we're finding the percentile. I think I made a joke about PPFs last time not being the production possibility frontiers. One of my other favorite ideas we have in economics. So all we're going to do is essentially plug into the PPF the actual percentiles we're looking for. This gives us the upper and lower bounds. So if I plug this in, I'm getting the lower bound, which is at the 4th percentile. And then I'm also plugging in the place I'm looking for on the upper side, which is the 96th percentile. If I define them as variables, it doesn't print them out, but you can just print these out. So lower bound, upper bound, and we'll print that out. Okay, so we know 92% of the population sleeps between these two values. Okay, any questions here? All right, this is the boring part of what we've done. What we're about to turn to, I think, is the big idea. Maybe in the entire class, and potentially even in like all of empirical science. I say it in a monotone voice, but it's one of the big ideas. Okay, so this is what we've done. We've talked about known distributions, but like I mentioned at the beginning of class last time, we actually generally don't know distributions. Like, you're looking at your data, you don't know what the distribution is that generated it. All you can see is the sample size, so how many observations you have. You have the sample mean, which is just, the average of whatever number you're calculating. And then you have this sample standard deviation. But the thing you're interested in, and you will be interested in your final project, is the population you're asking questions about. So, and these are things that we actually will never observe. So you'll never know whether the minimum wage increases or decreases employment. You'll never observe that distribution, but we can still make claims about it. And what we're about to do is the fundamental idea for how we were able to do that. To me, when I saw this for the first time, it looked like magic. Like, how would you ever know how to do this? Some statistician, actually a collection of statisticians in the 1900s made this realization. Okay, so we're starting concept 3.2. So exercise 3.1 is on Gradescope. I think some people have already done it. That's open for the end of the day. Okay, the interactive slides are... Okay, so I thought everything fixed today. So I guess I still do earn some lecture points, thankfully. So let's just, I'll fix that later. So what we're doing for the rest of class today is actually running a bit of a simulation. We're going to do 2 different simulations if we have time. So this is our big question for today. If all we see is the sample, what can we learn about a population? And the big realization is the one we're going to simulate. So you're going to run some data, you're going to collect some observations, I'm going to compile your observations in a data set, and we're going to learn some things about what's going on. So if we only see the sample, what do we know? Or what can we know? This is what we just did. We said, if we know the random variable, we can answer all these very precise questions about it. Like, we just asked the sleep time for the middle 92% of the population, and all these other types of things, like how many people sleep less than 5 hours and more than 9 hours. These are all questions we can answer if we know the population. But like I mentioned, the fundamental tension is that in general, we don't see that. We will never see that. Unless you're working with random variables directly, like statisticians sometimes do. So what we see is this sample. So what we're going to do first is this little exercise. We're actually going to roll some dice. We're going to roll some dice in Python. So I don't have enough dice for everyone in the room. So I have fake dice. We have Python. It's going to generate some random numbers for us. You're going to collect some data. I'm going to make some nice visualizations, and we're going to talk about what a lot of this means. There's a big idea, and we can just see it directly with some figures. Okay, so now we turn to exercise 3.2. How nice. This one also works. So we're gonna roll some dice. So hop over to. I'm actually gonna ask you for your numbers. So you will run some numbers. I'm gonna go around the room and ask everyone for some numbers. I get that warning because I forgot to save a copy in Drive. But once I do, I can run the imports. And the main import we're using today is from SciPy, so the scientific Python package. We're importing the stats module. And what I've done here is I've given you some code to generate a random number, a random integer from 1 to 6. So this is NP, so the numbers package, random, and then random integer between 1 and 7. We put 7 to say that that's the where we stop. So we stop at 7, which means we include 6. So 6 is our highest number. And then so we go from 1 to 7, and then we tell it how many observations to collect. So in this case, we're going to have a sample size of 1. So we're just going to collect 1 observation for each person, which is just rolling 1 dice or die. Is it dice or die? I think dice is both singular and plural, and then die is plural. 1 dice, 2 dice. Okay, we'll look this up and we'll figure this out. Someone look this up. We'll resolve this. So I'm going to run this. Every time I run this, I'm going to get a different number. If you don't want the entire array and you just want the item, you can just get the item, and I'll just give you the number. And every time you run this, it's going to give you a different number. Just like when you're rolling many, many dice, every time you roll a dice, you get a different number. This is the idea of a random variable. Every time we draw from it, it gives us a different number, according to the probabilities. Okay, so what we're going to do, I'm actually going to collect some data. So this is our sample. We'll call this sample 1. And we're going to actually collect some observations. So I'm going to go around the room. Each of you is going to roll your die, or dice. Did we figure out? Die. Die is singular, dice is plural. So I'm just going to put the numbers in. And we're going to plot this. And I think we all know what to expect here. This is going to be the most boring thing we do, or maybe second most boring thing. You all know exactly what this figure will show. All right? So my number is 4. I'm just going to quickly go around the room to keep things snappy. Just know where you are in order and just give me a number. 5.
3.
3, 2.
2. 6.
Skip. Yeah. 4.
4.
What was that? 1? 6. Okay, skip. Do we have some dice rolled? 4? 3. Okay, anyone I miss? All right, and is Gemini reading minds? No, it's just making stuff up. Okay, so this is our sample for a sample size of 1. You'll know what to expect here, right? If I plot a histogram, if you weren't making numbers up, Like if you were actually rolling the dice and not just telling me a number, we'd know exactly what to expect. So sns.histplot sample 1 and then Snapple sample 1. So this is, we have a small sample. This is, about 20. We have a bit of an outlier here, which is we have a lot of people saying 3. So my hypothesis is we have a lot of variation simply because we don't have a lot of people. If we had more people and I knew for sure that you were rolling dice, not just giving me numbers, I think this would look flatter. We can actually generate much more data if we wish. So I'm actually going to, let's call this sample 1, and then I'm going to simulate, should we say 10,000 die rolls? So I simulated 10,000, and if we plot that, it looks like this. So we'll say bins is equal to range between 1, 7, and so this looks, pretty good. So something like this. So this is, what we'd expect. If we have a larger sample, things will get closer and closer to the truth, which is even probabilities on everything. So we could even put, a larger sample if we wished. So as we increase the sample size to 10,000 die rolls, it gets flatter and flatter. This is what we know. The next thing we're going to do, you're going to roll 2 dice and take the average. I'm giving you some code here for, actually I haven't given you any code, just the sample size. But you can take the die roll from above and plug that in. So this is just, 2 dice. You're going to have to take off integer on the end, but every time you run it, you get 2 different dice. And if you want to calculate a mean, all you do is put mean on the end, and that gives you a number. And then I'm going to ask you for this number. Everyone clear what we're doing? All right, so I'm going to go around, we'll say this is sample 2, and you're going to tell me your numbers. So my number is 3.5, which is right in the middle. 5? Okay.
Yeah.
Is that right?
Yeah, that's what it says.
Okay. So 5. And think about this. So there's only one way to roll a specific number when we have 1 die. So if I roll a 5, I know exactly what generated the 5. It had to be exactly the die roll showing 5. But when Zach is saying 5, it could be a couple of possibilities. It could be a 4 followed by a 6. It could be 2 5s, or it could be a 6 followed by a 4. So like at least 3 different ways of generating a 5, because we're taking the average. So be thinking about what's going on with that. There are multiple ways to get a 5, multiple ways to get a 3.5. So we have a 4. So similarly, there are multiple ways to get a 4. And you could think about all of the different possibilities to get a 4. This is like somewhat less boring, but still we're in like boring range. All right, let's keep going. Average of 2 dice. 3, okay. 4.5, 3. Okay, so Mairead's number is interesting. There's multiple ways to get a 4, multiple ways to get a 5, but there's only one way to get a 1. It has to be exactly a 1 and then a 1. There's only one way. That's what you got, right? 2. So 2, we could have this happen in a couple of ways. We have a 1 and a 3, or a 2 and a 2, or a 3 and then a 1. 4.5. 4. 2.5. 3, 2.5, 1, 3.5, 1. So again, this must be two ones. Nice. 5.5, 2, 4.5, 2.5, 5.5, 5, 6. So two sixes must be. Yeah. 1, 2.5, 2.5 again. Two 2.5s in a row. 3, 3.5, 2, 5.5, 3, 2.5. And is that everyone? All right. And then Gemini is just making up numbers. So here's our sample 2. Now, without plotting this distribution, we're going to show both the sample we collected in class. Unfortunately, I'm a little bit worried that the samples we're collecting are a little too small. If we had full attendance, we'd have a much larger sample size. Maybe we should do this right after the exam next time. Think about what you would expect from when I plot this. Is this going to look like this? Or is it going to look structurally different? Be thinking about if there might be structural differences. So I'm going to just go ahead and plot this. So sns.hist plot. We have sample 2. And then let's set up the bins range from 1 to 8. So when I plot this, does this look uniform? Does this look like it might be because the sample size is small? Maybe. So let's check this sample against a sample of, like, let's say 100,000. So I'm just going to run sample 2, but instead of using the data we just collected, let's just run 100,000 observations and get the mean. Okay, so what does this look like? I mean, this is pretty close actually to what we collected in class, except it's maybe a little nicer. What are we seeing? Does this look like the distribution of die rolls? What's different about it?
Well, it's different from the first one.
Yeah.
Because it's like not flat.
It's not flat.
It seems like the normal distribution that like we tend to see.
So this is
I don't know
maybe,
what that's called.
yeah, so like it doesn't look like a uniform distribution with even probabilities on every value. Like there's more values in the middle. Anyone know why this is true? This is like an empirical regularity. In fact, we can show it mathematically. We can show it with a simulation. Why is this happening, Mairead?
Because if you're taking the mean of like random numbers, you're more likely to continuously get a number that's more in the middle.
Okay. Yeah, we're taking an average, so maybe it sort of draws us to the middle. Yeah. What's some other intuition here? Like what's going on, Zach?
Oh, also there's like less, like to get a 6, there's less ways, or like to get 1, there's only one combination rather than 3 to get 3. You know?
So if for me to get a 1 with 1 die, so if we're taking the average of 1, for me to get a 1, all I have to do is roll a 1. For me to get a 1 when I have 2 dice, I need them both to be 1. So it's like half as likely, right? I need both dice to be 1 for me to get an average of 1. So you can see the extremes are becoming less common. We've gone from 1 dice to 2 dice, and now the extremes are less common than before. We could do this again, If you wanted to generate a sample of 3, all you do is go up here and calculate a sample of 3 and get a mean. And you could do that. For the sake of time, I'm just going to simulate this. So I'm going to get a very large sample with an average of 3 dice. And we're going to plot the distribution. So if you want to do this for yourself, you can just follow my code here. So here we'll have the sample of 3, and then we're going to make sure this is a sample size of 100. It's 10,000. Let's make this 100,000. We're going to take the average for 100,000 times over 3 dice. So this is like 300,000 die rolls in total. I'm going to plot this distribution. And maybe let's change this to be smaller intervals. Okay, the distribution doesn't look nice, but we can do this. Okay, any questions here? What does this look like? Evan.
It's like a normal distribution.
So Zach was saying maybe like earlier, we had this thing where we had more data in the middle. Maybe it's not quite a normal distribution yet. Maybe if I take out the bin definition here, we can maybe see something going on. This is not a normal distribution, right? Like this is just, it's a pyramid. Yeah, Zach.
It also seems like the width is of every, like one is pretty thin, and so like
Yeah.
maybe they get smaller. So maybe it's like they're getting more specific to one number. Like if
Yeah, so there are more different ways that we can get averages when we have 3, right? Which is exactly the idea. So the bin widths are actually getting smaller. More possibilities on the horizontal axis when we're taking averages over large values, or larger numbers of die rolls. Here, there's no curvature. This is just a straight line going up one side, straight line coming down the other. Here, we're actually starting to see a bit of curvature. Like this is bowed in, and then there's this like curve shape over the top, and then it's starting to bow out. The same idea is applying. When we have 3 dice we're rolling, 3 dice, to get a 1, now it's even less likely. So the tails are becoming even thinner. If to get a 1 of 3 die rolls, it has to be 1 followed by 1 followed by 1, which becomes less likely. We get this sort of pressure towards the middle and away from the extremes. Extremes become less likely when we take larger and larger samples. Okay, can I show you a couple more? So let's do a sample size of 30. So originally this was pretty boring, right? We were just rolling dice of 1 and then taking the average. Then it was 2. Then it was 3. And now it's 30. So if I'm looking at a distribution with a sample size of 30, this certainly does not look uniform. This is not a distribution of die rolls. This is a distribution of something else. We're increasing the sample size. The extremes become very, very unlikely. It's very unlikely you're ever going to get a 1 when you roll 30 dice. Like, that just becomes very, very unlikely. You need 30 ones. So it's 1 over 6 raised to the 30 power. That's a tiny number. It may happen in our sample because we have 100,000 observations. Anyone know what this is? Or what it looks like? Zach said it earlier. This is a normal distribution, or it's getting closer and closer to a normal distribution. Okay, so we're pretending like we don't know the underlying distribution. We know it's uniform. But as we increase the sample size, the extreme values become less and less likely because we're taking these averages. And we get more and more probability placed on the middle values, because middle values become more likely when the extremes become less likely. This turns out to be exactly, or it turns out to approach a normal distribution. So I'm going to hop back over to the slides, and I just want to talk you through a few things. These are just some pictures in the slides to show what we've just done in the notebook. Here we have just the distribution. This is a very large sample. This is a uniform distribution for die rolls. Now if we rolled 2 dice, what we did is we took 2 observations, took their average, and then we plotted the distribution. So this is a sample of 2, and then we're just plotting the distribution over that. Many, many more ways to get middle values than to get extreme values. How many of you have played Settlers of Catan? No? Okay. I grew up on that game. You roll 2 dice. The most common outcome is a 7, which turned out to be a robber. And that's just because there are many, many more ways, many ways to get a 7, and it's very unlikely to get a 2 or a 12 when you roll 2 dice. That's what's happening here. And then when we continue to increase the sample size, we start getting this curvature, not just pressure towards the middle, but it turns out there's a curvature to it. The reason for the curvature is a little outside the scope of what we're doing in this class, but mathematically that's what happens. Okay, so every time we roll, we're actually collecting many samples, and then we plot them and get these distributions. It turns out these distributions are not exactly normal, but they get closer and closer to normal as the sample size gets larger. Not just some random distribution. This is a normal distribution. And the normal distribution is something we know. So in the world where we didn't know what the distribution of the die rolls was, we do now know the distribution of the sample means. And that's exactly what the central limit theorem tells us. This is the big idea. This is, we go from a world where we may not know the distribution. With die rolls, we actually do know, but most of the time we won't know. So in worlds where we don't know the population distribution, we will know the distribution of the sample mean, or at least what it approaches when the sample size gets larger. That's the central limit theorem. And we've just essentially simulated it in about 20 minutes. You've all seen the central limit theorem before? This is the reason it matters so much. Because in general, we will not know the population distribution, but we will know the distribution of the sample means. This is what we call the sampling distribution, the distribution of the sample means. The central limit theorem gives us the shape of this. It gives us the center. So the center of the sampling distribution will be on the population mean. So not only do we know the shape, but we also know where it's centered. And it's centered on the population mean. And we know the spread, which is this funny thing called the standard error. It's the sigma, which is the population standard deviation, divided by the size of our sample. So we have sort of 2 different things, right? It's the population parameter, sigma, which we won't observe directly. And then we divide it by the sample statistic, which is n. It's something about the sample that we just took. So we're sort of mixing terms. We're mixing the population parameter, sigma, dividing it by the square root of n. The reason it's the square root of n to generate the standard error is sort of mathematical. The full derivation is a little outside the scope of this class. But fundamentally, what this is doing is saying as the sample size grows, the distribution itself shrinks. And because it's centered on the population mean, mu, it's shrinking towards the thing we're generally after, which is the population parameter, the center of the population. So we get more and more certain as our sample size grows. Our uncertainty shrinks because we're dividing by the square root of n. So this is the full derivation. I don't really need you to know a lot of this. You've probably seen some of this before. If you're interested in like how we arrive at these things, there's like good mathematical foundations for all of this. This is not a class about those foundations. The fundamental reason is like when you take the variance of a bunch of, like you add a bunch of random variables together, the variance of the sum is the sum of the variances. So you just add all these things together, and then it's n of them times the variance, sigma squared. And then if you divide everything by n, then it turns out to be this. So it's n is the variance of the sum divided by the square of n. You don't really need to know so much about like why this is true, but this is how we arrive at these things. So the variance of the average is sigma squared divided by n, because one of these n's cancels. So then when you take the square root to get the standard deviation of the sample mean, the sum divided by n, when you take that square root, you get sigma divided by the square root of n. This is the derivation for where it comes from. If the reasons for any of these steps isn't clear, there are entire classes devoted to making these foundations work for you. But this is how we get there. Any questions about this? So even though you don't need to know the foundations of how the standard error for the sampling distribution is derived, knowing what the standard error is will be very important for this class. The standard error is the standard deviation of the sample mean. The sampling distribution. So the sample mean follows the sampling distribution, which is centered on the population mean and has a standard deviation that's equal to the standard error. And if you forget any of that, it looks like this. Normal distribution centered on the population following the standard error. Okay, any questions? Can I show you one more thing? Okay, we have 5 minutes. I think let me show this to you just to put a bow on what we've done today, but I'll have you submit your exercise next class. One last question you might have, like when we roll dice, we're rolling, the distribution looks very nice, right? Like it's a uniform distribution, it's symmetric. So maybe that's why we get this nice normal distribution of the sample means. So what if I actually give you an example of a skewed distribution? Will the central limit theorem work when we have a skewed distribution? Do y'all know the answer to this? Like if it's not symmetric, will the central limit theorem still work? Do y'all know? Okay, mixed answers. So let's actually simulate this. So I have a skewed population. So sometimes things follow other types of distributions like chi-squared. Things like wait times follow these skewed distributions. So what I'm going to do is simulate 1,000 sample means from a chi-square distribution, and then just plot the distribution itself. So we just have a sample mean over 1. So no real averaging here. When I run this, I'm getting, so this is just, I'm collecting a bunch of samples. I have, stats.chi-square, and then I'm getting the values. I'm simulating 1,000, let's do 10,000, and then the sample means over 1. This is definitely not symmetric, right? Like when I'm simulating wait times, it's very unlikely you get very extreme values, and it's very likely you get smaller values. This is just a classic way to measure waits. You're waiting for the bus, you wait generally a certain amount of time, and not that long. So you might be wondering, does this central limit theorem apply here? And the answer is yes. Let me show you. So this is with a sample size of 1. I'm going to increase the sample size to 5. So I'm going to make this n is equal to 5. And we'll look at this. So this is n equal to 5. And even though we haven't increased the sample size by a lot, we're going from 1 to 5. You can see this distribution no longer has all of those zeros, right? Like the small values are now becoming less likely. Just like the logic from before, rolling 5 ones is much less likely than rolling 1 1. So these extreme values now have become less likely. We've shifted more towards the middle of the distribution. We can take this even further. So if I go to 30, I'm now taking the average over 30 observations. The extreme values, again, become increasingly less likely. We get closer and closer to the middle. If I increase this to a sample size of 1,000, you're going to see this distribution. And this looks classically normal, right? Like this is a very normal distribution that's coming from a very skewed distribution. You can play around with this. Like you can go in, find the strangest distribution you can find in all these packages. You can even like write one for yourself, and you try this on your own. Take 1,000 observations with a sample size of 1,000, and you're going to get a normal distribution, or something that approximates a normal distribution. This is a big, powerful idea. We're going to spend a little more time with this next class, just to wrap this up. But this is the thing we're going to spend the rest of the semester using. This is, we don't know the population distribution, but we sort of don't need to. All right, I'll see you next class. Have a nice weekend.